Hello everyone. So today's topic is about the modern synchronous counter. Now in the previous lecture we have discussed about the asynchronous counters. So asynchronous counters are serial counters. They are slow. They are slow because each flip-flop can change state only if all the preceding flip-flops have changed their state. The propagation delay thus gets accumulated over there, and so it causes problems. If the clock frequency is very high, the asynchronous counter may skip some of the states and therefore malfunction. However, this problem is overcome in synchronous or parallel counters. Synchronous counters are counters in which all the flip-flops are triggered simultaneously, as we have discussed, by the clock input pulses. Whether a flip-flop toggles or not depends on the flip-flop inputs. Whatever input we may have, that is a J, K, D, T, S, R, whatever, we have the input in our hand. Since all the flip-flops change state simultaneously in synchronization with the clock pulse, the propagation delay of flip-flop do not add together, as in case of ripple counters, to produce an overall delay. In fact, the propagation delay of a synchronous counter is equal to the propagation delay of just one flip-flop plus the propagation delay of the gate symbol. So the synchronous counters can operate at much higher frequency than those that can be used in asynchronous counters. Synchronous counters have the advantage of high speed and less severe decoding problems, but it also has disadvantage of having more circuitry and that of asynchronous counter. Now, regarding the design of modern synchronous counter, we have discussed that a mod counter is that counter which is able to count fixed or stipulated clock pulses. So suppose if it is a mod 3 counter, so it will count 0, 1, 2, that is it will include 0 in that, and again it will go back to 0, as we have discussed about the mod counter in brief in the previous lecture. Now let us discuss about the modern synchronous counter. Now the methodology involved in designing a modern synchronous counter. As we have discussed, it will be complex. So first start. Number is the number of flip-flops. That means we need to first fix how much flip-flop is required to perform the model operation. So the first step is number of flip-flops. Find the number of flip-flops required. For a modern counter, the minimum number of flip-flop required is n. That means if n is the minimum number of flip-flop required, the relation should be that m or the mod should be less than equal to 2 to the power of n. So in this way you can able to first of all fix that how many flip-flops will be involved for designing the particular mod counter, synchronous counter. Second is the state transition diagram. Now what we should do? Now draw the state transition diagram showing all possible states. Note that we can also include invalid state in the state transition diagram. If the next state to invalid state is not mentioned, we take it 0, 0, 0. Okay. So that means if it is a mod 3 counter, it will be 0, 1, 2 and again 0 or otherwise. Third is the choice of flip-flops and excitation table. Select the type of flip-flop to be used and write the excitation table for the counter. An excitation table is a table that lists the present state, the next state and the required excitation of the flip-flop inputs. Note that entries for excitation corresponding to invalid states are taken as given here. So it means that once you have obtained the number of flip-flops, then you need to go for the transition diagram, or rather in some form the truth table. Okay. That means if it is there means 0 to 0, then after 0 to 1, then 1 to 2, and then 2 to 3, and so on. And again, if for a particular mod operation, it should return to 0, then at last we should write this to 0, 0, 0. So in this way, we should write the transition diagram or the transition table. Then we need to fix the present state and the next state. Okay, we need to fix the present state and the next state. Okay, and in the next step, we should go for the minimal expression for flip-flop inputs. That means we should go for K-map. So prepare K-map for each input of flip-flops in terms of the present state of flip-flops. Obtain the minimal expressions for the excitations of the flip-flop using K-map. That means after fixing the states, that is the present state and the next state, you need to find the required excitation of the flip-flop inputs. Okay, and then you need to get the minimal expression for the excitations using K-map. So that's step 4. Then step 5 is finally you go for the logical diagram. So connect the input to the flip-flop as per the simplified Boolean equations. So let us see a mod 3 counter here. So mod 3 synchronous counter. So how we? It's an example. It will be you will be able to visualize these steps in this example, or by this example. So you see here, consider a design of a mod 3 up counter using JK flip-flop. So now this flip-flops, it will be given. You can design accordingly. It has 3 states: 0, 0, 0, 1, 1, 0. As you can see here. Okay. As you can see here, mod 3, 1, 2, 3, so 0, 0, 0, 1, 1, 0, and again it is written back to 0. Okay. So now the steps involved in design are as follows. So we will just go as per the steps which has been taught to you in the previous slide. So step 1, number of flip-flops. Here modulus m is equal to 3. Now we have seen in the first step that the expression which you need to obey to find the minimum number of flip-flops was m less than or equal to 2 to the power of n, where n is the number of flip-flops. So keeping that condition in mind, you see here 3, we should put here 2 to make it 4. Okay, to make it 4. So that 4 is greater than or equal to, rather greater than 3. So this condition is valid only if you take n is equal to 2. That is the number of flip-flop required will be 2. So that is the first step. Number 2, state transition diagram. The state transition diagram with 3 possible states, as we have seen, it has 3 possible states. Okay, is shown in the figure. Transition of states from one place to other takes place when clock pulse is triggered. Otherwise, it remains in present state. Number 3, choice of flip-flops and excitation table. Now, JK flip-flop is selected for this design as it has been mentioned in the problem statement only. The excitation table of the counter is drawn as shown in the table. It will be shown to you. Now note that inputs J and K can be obtained with the help of excitation table of JK flip-flop. Also note that state 11 is invalid. So the JK inputs corresponding to this are taken as don't care. So let us go to the table finally. You see here. Now you carefully look at this table. You see here, this is the present state. What is the present state? 0, 0. Okay. And it is a mod 3 counter operation. So 0, 0. And next state is what? 0, 0 to 0, 1. You can see here. Next state is what? 0, 1. Okay. as you can see here. Then if after this excitation, if the present state is 0 1 in the next clock, it will be 1 0. Then again third clock from 1 0 to, you see here, from 1 0 to, it will reset back to 0, because it is a mod 3 counter. It will only rotate in these three states: 0 0 0 1 1 0 0 0 1 0 1 1 0 0 0 0 1 1 0 and so on. Okay, so this is all about the left side of the table. Now how to map it accordingly? See, now you see here. Now we know that we require 2 flip-flops. Okay, so 2 flip-flop inputs are what? G1 G0 and K1 K0, or rather G1 K1 G0 K0. So 0 FF0, flip-flop 0 and flip-flop 1. So 2 flip-flops. Now we need to fix this characteristic table. How to do that? Or rather excitation table. How to do that? You see here, we are now doing this for J1, that means the FF1 flip-flop. Okay, so how to do this? How we have got this J1 K1 as 0? Okay, so you see here, Q1 is 0, in the next state Q1 is again 0. So the transition is 0 to 0. So for 0 to 0 transition, it will be either no change or reset. So that means either JK will be 0 0 or 0 1. Either it will be 0 0 or 0 1. That means it will be 0 cross. Don't care. Okay. Similarly, you see here, from 0 to 1 transition, as you can see here, Q1 is 0 here, the next state is 1. So 0 to 1 transition means either there is toggling JK11, or it is a set condition, that is 1 0. So you can see here, either it is 1 1 or 1 0. That is 1, don't care. Okay. Similarly, from 1 to 0 transition, you can see here, either this can only happen, okay, present state is 1 and next state is 0. This can only happen if JK is either in toggling mode or it is reset. So that means either it is 1 1 or it is 0 1. So that means cross. So first flip-flop excitation table is finished for mod 3 operation. Now let us go for the second flip-flop. You see here, present state is Q0, next state is Q0. Okay. So you can see here, the change is from 0 to 1. So 0 to 1 is valid by either it is in toggling mode or it is set. So that means either it is 1 1 or 1 0. So that means 1 cross. Okay. Now next is 1 to 0. Okay. 1 to 0 can happen if it is in toggling mode or it is reset. So that means either it can be, it is 1 1 or it is 0 1. So that means don't care 1. Okay. So what is don't care here? I'm just repeating it. Maybe it is there in your mind. Still I'm repeating it. Don't care means whatever may be the value of J, if K is 1, this condition will be omitted. Okay. So that's the meaning of that. Now finally, if Q0 is 0 and again from 0 to 0 transition, it can happen if there is no change, that is JK 0 0, or it is reset, that is JK is 0 1. So that means 0 0 0 1, so 0 2. In this way, you have to complete the whole table, and therefore I was telling that the design part is little rather cumbersome compared to the asynchronous counter operation. Okay. Now let us go for the fourth step, is a minimal expression for flip-flop inputs. Now we construct the K-map for flip-flop inputs J0, K0, G1 and K1 in terms of present states Q1 and Q0. Now you see here, you have to present the K-map like this. Okay, as you can see here, K-map Q1, Q0, Q1, Q0, Q1, 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 Q0. So this is the K map for J1. This is the K map for K1. This is the K map for J0. This is the K map for K0. Okay, you see here. So let us see J1. Okay, so Q1, Q0, 0, 0. J1 is 0. You can see here. Okay, Q1, Q0, 0, 1. Q1, Q0, 0, 1. J1 is 1. Okay, so Q1, Q0, 0, 1. J1 is 1. As you can see here. Now 1 to 0. Okay, 1 to 0. In this present state, J1 will be don't care. Okay, so Q1, Q0 will be 1, 0. So for Q1, Q0, 1, 0. So this one. So as you can see here, this is don't care. For 1, 1 condition, as we have told in the, as we have we have seen that in the properties, rather the methodology, it has been stated there that if you don't find the table, the condition, like suppose if it is 1, 1 condition, which is not here, you simply take it don't care. Okay, so you just make a pair over here and you get J1 is equal to Q0. Similarly, you can get this likewise for K1, J0, K0, and finally what we get is J1 is equal to Q0, K1 is equal to 1, J0 is equal to Q1 but K0 is equal to 1. Okay, so now we should go for the finally logical diagram. So using the above minimized expression, the logic diagram of the mod 3 counter can be drawn as shown below. As you can see here, so we have seen, you see here, you see what we have got. We have got J1 is equal to Q0, J1 is equal to Q0, J0 is equal to Q1 bar, and rest all are 1. Okay, we will see. So as you can see here, J1 is equal to Q0, J0 is equal to Q1 bar. This is 1, this is 1, and this is synchronous, means both are driven by the same clock. This is Q1, this is Q0 output, this is Q1 output. So this is the logic diagram of a synchronous mod 3 counter. So in this way, we can be able to draw any mod counter using this methodology and the steps. You are advised to follow other mod operation using the same methodology. Thank you.